the webinar that will hopefully make it a little bit easier to watch than last week's webinar. I may try to go back and re-record some of last week's webinar and put that up to replace the one that we did last week because of the problems I was having. So with that, I'm going to go ahead and share my screen now. So where we last left off last week, I showed how I had made a bandgap circuit that was more or less following the challenge. It's not optimal, but it works. It works for tutorials. And so starting off, I have basically a clean slate here. I do not have a layout. If I were to click on Edit Layout, it says there's no layout for project. If there is no layout for the project, if I go to the Characterization tool, I can click on something like Area, and it will give me an area, but it's doing an estimate based on all the devices. So it is actually picking up all of the devices that are in the net list and generating a layout, generating each device and computing the area of each device without actually creating a layout. There was a help request comment over last week in which somebody asked, why is it that the width and height numbers don't multiply up to the estimated area? And the reason is that the estimated width is calculated from the estimated area divided by the maximum height, and the estimated height is calculated from the estimated area divided by the maximum width. So those two numbers can't be multiplied up to get the area. And if without an actual layout you try to do, for instance, a DRC error check, you'll get nothing. And there is such a thing as a LVS error pre-check, but it's not very useful at the moment. So as mentioned last week, the way you get an initial layout is you click on Edit Layout, like I did before, where it says No Layout for Project. Asks if you want to populate the new layout from the net list. You would say OK, and that would bring up the Layout tool. And what you get is whatever was in the actual schematic net list. And since Electric does not have any way to specify, for instance, that resistors should be a series link of a number of smaller devices, then the only way to specify a resistor in the schematic is just to give the total length. And since the tool that generates the initial layout is not especially smart, then that's what it's going to give you. If you've specified one very long resistor, that's what you get. Since a lot of these band gaps involve very, very large resistors, the layout will look even worse than this. If from here you go back to the characterization, regardless of whether it says this is coming from schematic capture or not, these physical checks are going to be done on the layout. And if I do now an area check it will be doing that area check on this layout, and it's going to fail because the area is ridiculously large, and that's because of these resistors. And if I do, say, window measure box, that's the value. There's the value down there that I'm getting in my characterization tool. It's just the total area, including all of this wasted space here. Likewise, my width and height checks are going to be done on the, sorry, wrong one. The width and height checks are going to be done on this layout as well. So the width is going to fail at 800 microns. The height is going to fail. One weird quirk about the tool at this moment, which is a bug that I have to fix, is that if you run DRC errors while the layout is still up, the layout actually has a lock on all the files, and it's going to fail to run DRC. If I want to find the initial DRC check, I'd have to pop down the layout, and then run the DRC check, in which case I see that it's failing. If you submitted it to ACE, ACE is obviously not going to have a layout running, so it's going to give you the correct DRC errors. So just make sure when you're running DRC from this characterization tool that you do that with the layout, without a layout up. So again, a slight recap of last week's. Is that if I go over here and want to floor plan, Control I will, no, not there. Control I will select the device, and key Q will bring up the parameters for the device. Here I have a device that in my schematic was intended to be I intended to have an array of equal size resistors. This one was going to be 14 times the minimum size device. The minimum size device is down here. And if I look at the minimum size device, it was supposed to be 39.8. You can take my word for it that the larger one is 14 times the size. I wanted 2 of those, so that's 28, and 2 of the smaller ones makes 30 total. If I want to refloor plan this, I can just go in and say I want an X repeat of 15, a Y repeat of 2, apply that. Now I've got, I can move that around. Now this is a much better aspect ratio. With that done, I can remove these devices. One thing to note prior to doing LVS is that, of course, this is a single device. These were 4 different devices and have 4 different device names in the schematic. Once I have, if I remove these, then the device names are no longer going to show up in the LVS. You can take certain measures to alleviate that. For instance, if I want to make sure that I know that this device here is representing both of these devices. Let's see, this one, let me zoom in on this a little bit. This device here is called, zoom in on it further. This one is called RW at 3. This one is called RW at 5. I'm going to be getting rid of both of those. So I can go over here. This one's RW at 2. If here's a command line thing, I can say identify, which changes the name of the device. So where it was XRW, RW at 2, then I can just sort of add on to that RW at 5, RW at, or I've already forgotten what the name was, I think it's 7, which has no physical effect on anything, but it will allow me when the LVS is running to better track what the error messages are. If they relate to this device, then I'll immediately know that, oh yeah, it may be coming from a comparison to the schematic for this device or the other device or the other device. In this case, the band gap is a pretty small circuit, and you probably won't have too much trouble tracking things between the schematic and the layout, even if you've changed the devices around. Now, the whole process of refloor planning this thing and doing an initial layout and wiring up would, of course, take hours. I think it took me a couple days to wire this thing up initially, so obviously I'm not going to do that in the middle of a webinar. What I have done instead is just to break this design up into different pieces. So if I move on to the next design, I'm going to have to close this window because this is effectively a new project. This is the result of several days' work, floor planning and wiring up. The result looks like this. One thing you might notice that I did not do when I was, or that is different from what I was mentioning in the floor planning, is that here I actually have an array of devices, an array of individual resistor devices instead of a single array. So there's a guard ring around every resistor, and since I replaced this from something that I had before that didn't have guard rings at all, I have ended up shorting together across all of my guard rings. That's clearly a mistake. There are a number of other mistakes that can probably be seen from just by eyeballing the layout. So this is going to be my first starting point for showing what the LVS tool does. I have a layout, so I don't need to worry about extracting it or doing all that. That's just what the LVS tool is designed to do. So I'm going to click on Run LVS and hit Run. And it is going to tell me that actually it would have, I think it did not create a netlist in this case because I already had one. But if it hadn't, it would have gone on and created that netlist for me from the layout. At the end of the LVS tool, this is what you see. It says netlist do not match, and that's what you're going to try to get rid of as you're working through the LVS. The whole LVS window, really all it is doing is it is printing out a file that's being generated by the netlist comparison tool called comp.out. If you look at the file system view, inside the project, there's a directory called mag. Down in that directory called mag, it has dumped all of the devices that were in this layout, and the extracted views of those are in the .ext files, and there is one file here that's generated by the LVS called comp.out. And if I just bring that up in an editor, it's just a large text output. Now, I generally prefer to look at the text output. You can look at the comp.out file if you want, or you can look at the nicely arranged version that appears in the LVS manager, which is what I'm going to do for the webinar. And there are three sections here. One is the initialization. That corresponds to what's up at the top of the file. All it's doing is it says it's going through, finding all the things that are unmatched, which largely means that it's flattening all of the wrapper devices, all the P cells or gen cells, as I call them, for each MOS and resistor device, because the wrappers don't exist in the schematic. It is also merging devices, so wherever it finds devices in parallel or in series, it will try to converge them up front before it does the comparison. And it's guaranteed to run into trouble there because I've shorted all my devices together. Not intentionally. So the second section then is the actual comparison. There will be one such section for every subcell in the circuit. In this case, it's just a flat device with, since the wrapper devices have already been flattened, then they're not being compared. So all I have here is just my single circuit for the band gap and a lot of low-level devices, which are compared directly, so they don't show up as lines here. So there's only one sub-circuit to look at. If I open that up, that's divided into three sections at most. The first one is a summary. That's the first thing you're going to look at. The summary is going to tell you what devices are in each of the sub-circuits for the layout and for the schematic. And if there's a difference between the two, then it's going to type mismatch and the result is going to show up in red. In this case, I have managed to get the NMOS devices correct. The RW devices are resistors, and there's a definite mismatch here, and I can tell you that comes from all the shorting that's going on with the metal here. Because here there are 10 explicit devices that are put in the schematic, but here they have been split up and some of them have been recombined in series and parallel, but clearly there are mistakes in here that need to be corrected. So this is the first line that you need to be looking at in LVS. Make sure that you look at the summary, and you're going to have a hard time understanding what's going on, particularly in the net mismatches, as long as you have mismatches in the number of devices. So do what you can to get the number of devices equal first. Likewise, here you can see that it says there are 2 bipolar devices. That's obvious for a bandgap design. You're going to be, you have two bipolar devices, but one is a multiple of the other in terms of emitter area. But in my layout, it's telling me I only have 1 device. That means that it has shorted them all together. If I go look at it, here I can this is going to be the most useful command in Magic to use for this, which is to take the S key for select and hit it twice to get a group, hit it 3 times to get an entire net. So this is selecting the entire net. You can see that it was designed such that these 2 in the center are supposed to be on 1 net, and all these 2 around the outside are supposed to be on another net. And you can see, because it highlighted the entire net, that not only are both of those nets tied together, but they are also shorted to the power supply rail up here. So that's clearly an error that will need to be fixed. For now, I'm going to ignore the PMOS device mismatches. There are a lot of things to be fixed here. And since that is a fairly major task, again, that's something I'm not going to do here. I'm going to try to get the LVS to a reasonable state in some fairly large steps where I leave out a lot of stuff. And then from here, I should be able to show you an LVS that's reasonably clean enough that I can get there from here, working in real time during the webinar. So now I'm going to go down to my number 2. All right, so having worked on that, it took me about an hour and a half maybe to rewire all of that stuff from the mistakes that were in the other view. And you can see the main thing I did there was to replace that array of resistors with 1 single device, as I showed earlier on. That gets rid of all of the guard ring contacts between the devices, so I have all the area in between to route things, and I was able to clean up my nets there. Again, looking back at the networks for here, I've resolved the issue with the short to the power supply. So these 2 devices are only connected here, and the other network for that is connecting together the rest of the devices. So there's a ratio of 2 to 10 here, and there's no longer a short. So with a number of those things fixed, let's see what the LVS says. Again, I'm going to run. Oh, there I did not have a net list. So when I ran, it said it was generating the net list for the layout automatically. Again, I get net list do not match, but let's see what it is by expanding this. Again, looking at the summary. Okay, so all the work that I did to remove all the shorts from the resistor area, in fact, has resolved all the problems with resistors. Now I have 10 resistors in my schematic, and after serial and parallel combination, I've got 10 resistors in my layout. The NMOS devices are fortunately still correct. The bipolar devices, I've got 2 and 2, so they're good. PMOS devices, I still have, apparently one of them got resolved by removing shorts and things, but I still have a device mismatch. So now I'm going to show you how to track down things from within the LVS tool. As I said previously, the first thing you want to do is make sure that all of your devices are matching before you start getting into the net mismatches, or the net mismatches are going to be very difficult to work through. So the first thing I'm going to look through is my device mismatches. Whenever you open up one of these that says either device mismatches or net mismatches, it's going to give you a series of groups. This is related mostly to the algorithm that the LVS tool uses to do matching. It will divide all the devices into groups based on their fan-outs, and as it refines those groups, they will eventually either drop into one device in layout and one device in schematic, which is a match, or there'll be several devices in layout and several devices in schematic that don't match, and those will get dumped into an error group. So here is one of those cases. I've got an instance that shows up in the schematic. It says that this is instance PMOS M5, and in the schematic I should be able to go back and find that device. And it says that there is no matching instance in the layout, which makes sense. It says I've got 19 devices here, I've got 18 devices here, so apparently one has gone missing. I probably deleted it by accident. So here I can go into the edit the schematic and go find that device, M5. I'll save the trouble of searching for it because I know where it is, but M5 shows up here. It's one of these digital MOSFETs that's part of one of the inverters that drives the digital or the power down. I do happen to know from doing the layout that I put all the digital circuits up in the corner. So they all appear up here. And if I go there, it is very obvious now that there's one missing. So yeah, that's where it got deleted. So let's go take, I'll just take this one and copy it. And to get rid of the DRC errors, I'm going to use the arrow keys to move it over until it matches. Okay, there we go. And since it looks like I had it all wired up before I accidentally deleted it, all the wires are still in place. I'm just missing one connection here from the guard ring up to the power supply, which I can go middle click there to create that connection. Now I'm going to save, auto write. Now I can just run the LVS again. And go back to the summary, and there. Now my PMOS devices are all correct. I've got all my devices matched between layout and schematic now. And so, because they all match, there's no device mismatches listed down here. So all I have left to look at is net mismatches. Now here's a case in which the net mismatches give you several devices in each group. In this case, there's several devices, several nets in the layout group and fewer nets in the schematic. That would normally be an indication that I've either broken a net in the schematic or the schematic is shorting a net in the layout. Normally, if assuming that you have been doing simulations with your schematic net list, you can assume that all of the errors are going to be in the layout. So since there are more nets in the layout than there are in the schematic, I must have broken a net somewhere. So let's take a look. Some of the nets are named. One thing that, of course, the automatic generation of layout doesn't do is it doesn't create any of the nets for you. So unless you go through labeling each of your nets to match the ones in the schematic as you draw it, then you're going to get these made-up names from Magic that is basically telling you some position of the net. And then these are the names from the schematic, also automatically generated from electric. So I'll concentrate on this one, VDDA. So what is below it? Well, this is a list of all the devices that are connected to that net. Each one is listed along with the pins of the device that are connected to that net and the number of such pins that are connected to that net. So what this says over here is that the schematic has a net called VDD33A, of course, and connected to that are 12 PMOS source or drains. This little vertical bar is an indication that the nets, the pins 1 and 3 are permutable, so you can't tell the difference in a FET layout between source and drain. So that says that there are 12 devices, either source or drain, for PMOS that are connected to net VDD. And pin 4 is the bulk connection. Of course, the bulk connections of all the PMOS devices are again connected up to VDDA. There's one NMOS source or drain connected to VDDA that might be an alert in some cases. In this case, there is actually the schematic a MOSFET source that's connected up to VDDA, and two resistor devices of RW. Again, the ends of resistors are exactly alike, so they're permutable. So it's either N1 or N2, doesn't matter which. Two of those are connected to VDDA. So how does that compare to the layout? Well, the layout, okay, there are two resistor devices that matches, one NMOS device that matches, the 18 PMOS bulk connections matches, the 12 PMOS source drain connections, though there are only 11 here. So I'm missing, VDDA is missing a connection to some PMOS source or drain somewhere. Best place to go looking for that is further down in this list. So if I look down here, yeah, there's this net right here. It's got a connection to one PMOS source drain. In fact, any net that's listed in your netlist dump here that has only one connection anywhere is almost certainly a isolated, unconnected terminal, because pretty much everything is going to be connected between 2 points. The only exception would be an output pin. So unless the net happens to be one of your input pin. So unless this is one of your input pins, then it's pretty much guaranteed that this device here has gotten unconnected from the rest. Now, how to go find that in the layout? Ideally, I'd have you click on this and it would go directly to the layout. That's an inter-process communication thing that I have not yet gotten around to implementing in this tool. So for now, it will be manual, but you can just go down here to the layout. If I can get both in the view at the same time. The net is M1, so I'm going to say go to, G-O-T-O, go to, and then type in the name of the net, 2971_1170 pound. And it tells me metal 1, that means it found it somewhere. If I want to find where it is, just press the Z key, zoom to, that zooms to the place that was just selected. I can move out and yeah, there it is. And it's definitely a disconnected net. Obviously, I started routing that and never finished. It's supposed to be connected to VDDA. VDDA is the bus up here. So I'm just going to go to the wiring tool, click on that. That catches the metal 1, drag it up, connect to metal 2. That caused a little DRC notch error there, if you see. So I'll just draw over that, and that gets rid of the DRC error. I'll clean that up a little bit. Okay, so that should get rid of that one. Let's see. I'll do another save. It's really easy to go just do it, save, and run the netlist tool again. So run. And summary still says all device matches. Nets. Yep, the net list has gotten a lot shorter. VDD no longer appears on there, so that has been taken care of. This one now, I've got 6 devices over here, resistor. Here I've got 5, here I've got 1. Again, it looks like if you combine this net and this net, you get the same count as this net. So once again, I'm going to have to, in this case, I'm going to have to go find both nets because I don't know where they are. Unlike VDD, I'm not immediately aware of where this is, so I'm going to say again, go to M1-267-1046 pound. Z key to zoom to that. Go zoom out a bit, and okay, here, whoops, zoomed out a little bit too far there. Let's see. Here is one of them. Looks like a normal enough net, so can't really tell where are the rest of them. I'm going to highlight this. I'm going to type in select feedback. That's going to leave that net highlighted while I go find the other one. So the other one, go to, it was, see, I already looked up that one. So it's M1-35558-872 pound. Again, Z to zoom. There it is. Zoom out. Okay, it's all of these guys here. So I'm going to do that. Select, catch that, select, select, select. There's, whoops. Select, select. That's the whole net. And you can see, okay, there it is. Obviously, there's the other net. This is the net. They're obviously supposed to be connected together. I'm going to remove my feedback now by going up to Layers, Clear Feedback. Obviously, I would want to put a via there. So via, go to the wiring tool, pick up that metal 2 line, drag it up here. All right, now I've connected those nets together. Back to save. Auto write. Back to the LVS tool, run again. This time it ran. There's nothing here saying net mismatches. That means I've got a complete net match. So let's take a look at it. It says, yes, net list match uniquely. That's what you want. But over here it says there were property errors. So that's the next step. Once you have, so the first steps again are you get all your devices to match and the number of counts, and you get all your nets to match, and then you go looking for property errors. If I look at all the property errors listed here, they are all RW resistors. And you can see this is what it's saying for the layout, what it's saying for the schematic. And let's take a look at, like here, this one that's 00545, that's that huge resistor. So the question is, why is it saying that this is larger than, or the one is not, yeah, this one is saying that in my layout it's 560 microns long, and in the schematic it's 545. So for that, I'd have to go back, see what I had put down for that resistor and why is it different. So if I go zoom in on this device, see which one is it. Here it is. This is one of the two big ones. Yeah, 0.545. If I click on it, oh, I have to select. Click. It is supposed to be width of, well, the total width is 544. I guess I can't really tell much beyond that. Yeah, it was 14, so what was it? 545, and I'd split it up into 14. No, wrong way. 545. I'd split it up into 14 devices, so each one should be 38.9. And if I go to my layout and look at one of those resistors, it says the length is 40. Yeah, well, obviously I got that wrong. So let's go correct that. I'm going to change this resistor to 38.9. And there it is. Now that caused everything to be off center, so I'm going to move everything up. Not that. So if I move it up to about, well, too far. There we go. Watching my DRC count over here, I'm going to need to fix some errors. But most of those were just caused by the fact that I shrunk my layout for the resistors by a bit. So I'm going to catch all those here with the A button to do an area, and I'm going to do stretch north 20. Yep, that fixed that. And since I centered that, then it's going to need stretching down from the top. So let's do that. Stretch south 20. Okay, that looks like, yep, my DRC has gone down to 3, so I've corrected most of those errors down here. It looks like I managed to cut a contact. So and I also made that metal too small. So click on that. And this whole thing is a little bit too close to that other metal line, so I'm going to stretch that. And now I'm back to 0 DRC errors, and I fixed those resistors. So since it's very easy to do a save and recheck, I'm going to do a save and recheck. Run again. Go straight to the summary. Yeah, my list of non-matching devices is still there, but it's a lot shorter than it was before. Looks like the rest of my resistors are not quite right either. I've obviously done some bad resizing of resistors. Let me go check these. There are only so many resistors in here. So this one is 17.4 by 3. These are all the resistors that were part of my trim. So let me go find those. And it looks like, oh, I had everything here in multiples of 15. So they're supposed to be 3 by 15, but here I have 3 by 17.4. So I'm going to change all those to 15. And once again, that means that it's shorter. It is no longer connected in a few places. Let me move that up. Actually, I think I will just, yeah. Move all that up. And then all I need to do is take this, which I'll capture with the A, use Shift S to collect the other ends of that, and then stretch that about 20. Yeah, that'll do it. Well, it looks like I'm a little too close to this side, so just a quick move over this way. And I've got 2 DRC errors, which come from, looks like down here. So I just need to move that out of the way. Okay, DRC is back to 0. Save, auto write, run. Oh, netlists do not match. I have shorted something here. Well, yep, I can see it right there. Yeah, this was supposed to come up. I was about to go find one of my saves, but it looks like I can fix this in just a little time. So there we go. All right, that should do it. Always annoying to have a properly selected netlist. Okay, there we go. Got one more property error, but now also take a look at this. I've got, even though the rest of it seems to match, it's got telling me there's a mismatch of pins. Obviously I've reversed my trim bits because I've got trim bit 0, 1, 2, 3 over here claiming to match trim bits 3, 2, 1, 0. So let's take a look at both of those errors. This one is, that last resistor in here is still not quite right. Where was that resistor? Oh, it looks like I put the wrong size resistor in here. This one is a 38.9 by 5. That's not right. I have got to zoom out here. Where was that resistor? Oh, is this going to come back? Oh. View. How do you get the full view here? Yeah, I have a slight problem with my mouse wheel not working. Can somebody tell me the command to get the
That
whole view?
zoom icon, uh, top menu bar, fifth icon, yeah.
Oh, the zoom icon, fifth icon.
One to the left.
I'm sorry, one to the left.
Yeah, yeah, that one.
This one.
No,
Sorry?
you can go to view and then on the top, yeah.
Oh, view control?
No, sorry. Window. I am sorry. Window.
That's right. All right, window. Yes.
Yeah.
Oh, there we
Zoom.
go. Fill window. All right, thank
Yeah.
you. All right. Sorry, you can tell how that I'm not all that familiar with the electric. And I also need to fix my mouse. Okay, yes, all right. Yeah, that one last resistor was not supposed to be the same size as the others. It was supposed to be 34.8 by 3, so 34.8 by 3. And I'm going to fix that just by moving this down here, move, well, I'm not going to do that. Wow, this layout gets really slow when it's with doing this with the zoom. Get that out of the way, reconnect that. And since I only have one DRC error, let me just fix that. A little extra metal here. Not to belabor the point. Okay, now I think I have all my devices correct. All right, now back to those pins. Yeah, okay, so I had those pins not quite right. So 0 needs to be swapped with 3. Let me try doing that this way. And 2 needs to be swapped with 1. Now, I am not going to spend too much time cleaning all this up because we're almost finished and it'll just take up extra time. So there we go. Just paste over that. I've already forgotten. Did I do that right? I think I did that wrong. Which one was this supposed to be? Was this supposed to be 2? I think 2 was already up here.
2. That is 2. Yeah.
That's supposed to be 2?
No. Yeah. No, you're right.
I'm not sure. But anyway, we'll find out soon enough. One thing, note, I accidentally got metal outside of the label. Labels do need to be connected completely over to the metal that they are, or it's going to cause troubles. You notice that it just says it just moved the label to space when I accidentally deleted the metal out from under it. So always make sure that labels like this are completely covered with metal. All right, let's run this one more time. And okay, yep, I said I'd. All right, first off, you can see all the errors for device sizes are gone. So I no longer have any property errors. And yep, I was right. It was 2 and 0 still wrong. I just got lost in this. All right, 2 and 0. If you will give me just a minute to fix this up, I really do want to show you a real correct LVS result. And also without DRC errors. There we go. Okay, so we've got DRC error 0. Labels connected. All right, fine. Save that. Back to LVS. Run. And hooray. Yes. Okay, there you go. That is what you want to see. To have a completely LVS clean device, it should say the cell pin lists are equivalent. It should say the device classes are equivalent and circuits match uniquely. And that is a correctly verified circuit. So I can close off my LVS window now. I can close out my layout now. Close out my schematic, don't need that. And so back to characterization. So I have a layout now. It's verified, so I should be able to run characterization. So let's take a look. As far as extracting the layout, this will do it automatically. So let me, but here I have this new button up here that tells me, do I want this from schematic capture or layout extracted? So if I want to look at the simulation based on the extracted layout, I would go up here, select layout extracted. Then let me choose a quick one. So let's look at VBG trim setting -1. Takes only a few seconds to run. And I get an answer for that. Now I can go back and forth between layout and extracted and schematic extracted. However, if I don't want to lose that data, I need to go down here and say save. Now I have saved the characterization results for the layout. I can then go back to schematic capture. Okay, there we go. You can see the difference now. This is the difference in the performance based on parasitics. With the schematic, no parasitics, I've got an output of 1.301 here. And with the layout, 1.304. So that's the difference. And obviously you would want to go with layout extracted, go through, do the run all, get all your results with the extracted net list. And regardless of whether this says layout extracted or schematic capture, if you do submit, if you have a layout, the layout is going to be submitted and the characterization remotely is going to be run on that layout. So it is in your best interest to make sure that that you have a layout LVS check. Of course, once I have done the LVS, it will run through that and it looks at the last results that were from that comp.out file. And so if it passes, then you should get a 0 pass down in this LVS check. Likewise, for the DRC errors, it's going to go match it up to what Magic said was the DRC result. There you got 0 and so forth. And my final circuit had this area, and I believe it was just a little bit too wide. Fails this by like 2 microns. But anyway, those are all the results. So that's how you get your circuit LVS. That's how you get the layout extracted and back into the characterization tool. The one thing I have not shown, and that's largely because I don't know how to do it yet, is to take the extracted layout that you have, which is going to be a spice file in the .mag directory, and then use that in Electric for simulation, for your own local simulations. So I'm going to leave that for the next webinar, and that I hope we can get out next week. So that ends my demonstration of using Magic and using the LVS tools. And if you have any questions, I will open it up now for questions.
Hi Tim, I have a question on
Sure.
doing LVS with the snake resistor. So because it's a snake resistor, the value of the L that you mentioned in the schematic and the value of the L that you mentioned in the layout will be different to get the same resistance in both schematic and layout. So how does LVS work for that?
Yeah, that's yeah. The snake resistors are an interesting one. Oh, excuse me. So what Rishi is asking about is the snake resistors. I was working a lot of last week to put these in. So if you bring up the RP1 device, one thing it gives you now that it didn't before is use snake geometry. So if I said I have a length of 10, say a width of 0.35, and I'm not using a snake geometry, and I create that device, then it's just a single device. The length of that device is equal to the length given here, which is 10 microns. So the box here, measure box, is 10 microns high. However, if I do a snake resistor geometry, pardon my phone. If I want to do a snake resistor, I'd want, for instance, a number of different turns. So the X repeat here is the number of turns. Say apply, I get number of turns. Now, however, I've got a length that's not actually the full length of it. There is an effective length. I would like to put that in. If I can get that into this in the next week, I will go ahead and post that update to the production platform. Right now, what you get, this is a sort of, well, I wouldn't say it's useless. It's actually the length of the resistor on one of the interior turns from for the length of that, excluding the endpoints. So this is just about 10 microns right there. Okay, 10 microns. Now you're probably going to want to match the effective length against what's in the schematic. Right now, I can only tell you try to get the value to be the same, because this value is the value of the complete resistor from end to end. So I would say adjust the length and the number of turns until you get the right value that matches the schematic.
Okay. So if the value, if the value is same in both the schematic and the layout, I'm fine for now, right?
Not quite. It will be close, particularly for a very long resistor. It should be close. The one in the schematic doesn't take into account the some slight effects of the S-block layer at the endpoints and the terminal resistance, some of which is contained in the model. So I think that, yes, for now, just go ahead and do it by value. You may have to go back after you look at the LVS results. If it's differing more than by 1%, then it will flag an error. You may have to go just tweak things just a little bit to make them match. But as I said, I am going to go put in this optimization or this extension where it will show you the effective length of the whole resistor. And then once I have that done, then you should be able to just match the effective length in here versus what you have in the schematic, and that should be enough.
Okay.
Yeah, sorry, that's a bit more long-winded answer than than it should be, but yeah, that's one of, putting in the effective length is one of our known optimizations that we need to do, and just have not had time to get around to it yet.
Okay. One more question.
Mm-hmm.
Let's say we have metal 1 and metal 2 on top of each other overlapping. So if I put a label, to which net does it get assigned to?
I'm not quite sure. Do you have a sort of example to give? In Magic, of course, all the networks, unless they're inside subcells, it's all just paint. So once you paint one net over top of another one like this, if metal 1, then they are just simply connected. If they were labeled, then there is some kind of rule in Magic. I think it's by alphabetical order, maybe, or by, actually there's a set of different rules that are somewhat complicated. But if you
no, Tim, this was not my question. So
okay, sorry.
Let's say the vertical one was metal 2.
Oh, I see.
And you label it in the intersection.
Oh, if you oh, I see. I got it. Right. The answer is, so you're saying, okay, what if you label it here? Well, first off, if I just simply said label, then it will do an automatic connection to the highest level. So here it just said moving label test from space to metal 2. So it just attached it to metal 2. And I can tell that it's connected to metal 2 by selecting the metal 2 line, and it highlights the test along with it. Whereas if I selected the metal 1, it doesn't highlight that. However, if I use the sort of, I would call recommended method to make a label, I would be going down here to text, and I would say my text string is test, and that then I can say, instead of saying attach to label default, just set it to metal 2. And then it should be attached to metal 2.
Okay.
Again, if I chose the default, it would do what it did here. You would see it say, not that, but you would see it say where it did before that it is moving the label test to whatever layer it decided to put it on. And if that's not the layer that you want it attached to, then you need to go through and do that, which is to select the layer that you want it to be attached to.
Okay.
So, are there any other questions?
So just one more question on the last point that you covered about the extraction. So currently we are not able to extract subcircuits and simulate in electric or vice versa, right?
There is a way to do it. I will have to get together with the people who know how to do that and work up a webinar for it.
Okay.
Jay might be able to tell you.
Okay.
Jay, do you know the method to do that? Actually, I don't know. Jay might not even be on the webinar. Okay. But yeah, we will work that up.
Hello? Yeah.
Oh, yes.
Okay. Could you just repeat?
Well, the question is, how do you get a subcircuit, a netlist from the layout back into electric for use in a local simulation?
A subcircuit from layout back. I'll have to look it up.
Yeah, that's
there,
what
there was a hierarchy tree, but yeah, I'll have to look it up. Yeah.
Yeah, we've done it before. We just need to update ourselves on the method and then get you a webinar to show you how to do it.
Okay.
If you don't want to wait for the webinar, send us a help ticket. We'll work you through it.
Okay. Thanks.
All right.
And Andre has a question. Like, he has asked if, I'll just read out, I'll just quote him. Are there any extraction settings like C only, RC, etc.?
Not at the moment. Right now, I am setting it to the defaults for the minimum value of capacitance that it will extract as a parasitic, which I believe is 1 femtofarad. If that is not a good limit, then we'll change it or put a setting in the LVS tool that will allow it to allow you to choose the one that you want. There aren't that many selectable things for the extraction. The limit of the capacitance that it extracts parasitics for is one of them. Well, if there are no further questions, then I will consider the webinar done, and we will get back with you, say, hopefully next week with another webinar in which we will finish up everything to do with layout and tell you how to do those extractions of the layout and put them back into your simulations. So thank you for attending, and we will see you again at the next webinar.
Thanks, Tim.
Okay, thank you.
Thanks, everybody.
Thank you. Take care.
Bye.
Andre, if you're there, sorry, I did not see the chat message. Let me reply to you in an email. Your question are there any extraction settings like C only, RC, etc.? So I'll follow up through an email. Okay, thanks.